My name is Ursula and I'm with the College of DuPage. Today I'm going to be talking about the concept of limiting reactants. So limiting reactants is a concept in chemistry, but today I'm going to be talking about it in terms of a recipe so that I can explain it better to everybody so that everybody understands what we're talking about. So when you want to combine things together to make a product, or in this case a batch of cookies, you have to have a recipe. So in chemistry, you would have a chemical equation. It's the same thing as a recipe. In this case, I just kind of made this up. This isn't a real recipe. I just kind of have just the basics of what a cookie recipe would have. So in this case, we're going to combine 4 cups of flour, 3 eggs, and 2 cups of sugar, right? Don't try this at home because it probably won't taste very good because we're not going to put in all the other stuff. This is just the basics. So, and then I checked my pantry, and what I have on hand, I have 8 cups of flour, I have a dozen eggs, and then I have 6 cups of sugar. Okay? So this is what I'm going to need to make one batch of cookies. This is what I have on hand, and I want to figure out how many batches of cookies I can actually make. Okay? So, being that I need 4 cups of flour to make one batch of cookies, and I have 8 of them, that tells me that I can make 2 batches of cookies. Okay? If I need 3 eggs for each batch of cookies, and I have 12 of them in my pantry, that means that I could potentially make 4 batches of cookies using if I use all these eggs. And then if my cookie recipe calls for 2 cups of sugar and I have 6 of them in my pantry, I could potentially make 3 batches using these 6 cups. Okay? Now, the problem is that these are all different numbers. So how many batches of cookies can I actually make? Well, I can only make 2 batches of cookies, right? And the way that you know this is because once you're out of the flour, that's it. There's no more cookies. You could have like 300 eggs, right? But once you're out of flour, that's it. The cookie making stops, right? So what this means is that the amount of flour that we have limits the amount of cookies we can make. So that's what's called the limiting reactant, or in this case, the limiting ingredient. The amount of flour limits the amount of cookies we can make. So we call this the flour is limiting, right? Or the flour is the limiting reactant if it were a chemical reaction, right? Or LR. Like when you take your chemistry classes, they'll say it's the LR. So the flour is the limiting reactant, the flour is limiting, right? And you cannot just go by numbers, because if you look in your pantry and you have 8 cups of flour, 12 eggs, and 6 cups of sugar, you might be tempted to say, well, 6 is the lowest number, so it must be 6. But that's not how it works, right? Because you have to look at what the ingredients are. This is a 4 to 3 to 2 ratio, and so you have to take that into account also. And so just because 6 is the lowest number, you can't just look at the numbers and say, well, it must be 6 because 6 is least, right? You have to look at how the numbers are related to each other. These are the amount of batches you can make. This is the least amount. This is the limiting reactant. So flour is a limiting reactant. It's going to determine how many batches of cookies we can make. Once the flour is gone, the cookie making stops. Okay? I'm also going to show you how it works in the case of the Skittles. Okay, so here we have a bag of Skittles. And if you remember the tagline, Skittles are taste the rainbow. Right? So in this bag, we have the rainbow colors here. So we have red, orange, yellow, green, no blue, and then purple. So we're going to see how many complete sets of rainbows we can get. So whichever color runs out first, that's going to be our limiting reactant. That one will limit the amount of complete rainbows we can get. So I'm going to open this bag, and then we're going to sort them and see how many complete rainbows we can get. Okay, so we have red, orange, yellow, green, no blue, purple. Okay, red, orange, yellow, green, purple, red, orange, yellow, green, purple. There we go. So no more orange. So that's it. So orange limits how many rainbows we can make. So in this case, orange was a limiting reactant because here, yeah. So there's no more orange over here. So we're out of orange. So in this case, orange was a limiting reactant. So in this bag of Skittles, orange ran out first. Orange is a limiting reactant. We were able to make, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. 28 complete rainbows. And that's limiting reactants. Today we're going to be talking about soluble versus insoluble. So the word soluble means able to be dissolved, especially in water. So what I have right here, I have some Skittles, and I just put them in a white bowl. I picked the dark purple ones so that you can see the S better. So you can pick any of the Skittles, but I just picked the dark ones because the contrast is better. So what I'm going to do here is I'm going to put some water in this bowl, and I'm going to pour it down the bowl nicely so that my Skittles don't get disturbed, and we're going to see what happens. Okay. So the other word that we need to know is the word insoluble. So insoluble is incapable of being dissolved. So we're going to see if any of this is incapable of being dissolved. So we should know that sugar, which is what the basis of the candy is very soluble. So if you know from the summertime when you have your lemonade and your Kool-Aid, when you mix it with water, if you stir it, you get your Kool-Aid mix, your lemonade mix, and it dissolves really nicely. You don't have all those grains at the end. The Skittles are mostly made out of sugar too. And so when you put them in water, you can tell, like here, the purple is coming off. You can see the candy inside, the sugar inside, it's starting to melt, it's starting to dissolve. And if I start to play with them a little bit, you can see the sugar swirling off. But if I touch them, you can see the S is still there. The S isn't going anywhere. The S isn't being dissolved. And that's because the S itself is not made out of sugar. The S is actually a wax. And so the wax itself is not soluble. The wax is insoluble. And so it stays like that. And if you wait long enough, you'll see like it comes off in little pieces. And see, you can there's the S floated away right there. Because that right there, that's a little waxy piece. And so that is the insoluble part of the candy. And so that's an example of soluble versus insoluble. Today I'm going to be talking about the candy pult that my husband and I made for Halloween of 2020. We wanted to pass out Halloween candy, but we wanted to do it in a socially distant manner. So we made a candy pult which launched candy at about 10 to 15 feet. So what we did was we went to the hardware store and we got some PVC pipe, 1 inch. And we made this right here. These pieces right here are 2 feet long. So this right here, these right here, these are 10. So there's 10 2-feet pieces and then 1 3-foot piece. This, the launcher actually is 3 feet. So there's 10 2-feet pieces and 1 3-foot piece. And then we have the little elbows here. There's 6 of them. So there's, let's see, 1, 2, 3, 4, 5, 6 elbows. And then there's 4 T pieces. So there's going to, well, I'll show you. So there's going to be, there's this one here, there's that one there, and then there's 2 over there on that side. And then we have this T, which is a little bit bigger because you'll see there's a space here because this has to swivel. So these are 1-inch T pieces. So there's 4 1-inch T pieces, and this is 1 1/4. And then these are the 1-inch elbows. There's 6 of those. It was cheaper to buy them in a tub. So here's the 1-inch elbow, the 1-inch T. And then we had a bungee cord here. So just whatever kind you want. You want it to be pretty stiff. And then just an ordinary spoon from the kitchen. And then you're going to need an additional 4-inch little piece of PVC pipe in there. You don't need any special tools or anything other than your hands to put it together. If you get the 10-foot pipes at the hardware store, you can ask them to cut it to size for you. Or if you have this kind of tool, you can cut it yourself at home, which is what we did. You don't need to glue the pieces together. You can leave them like that. I would tap them together with just an ordinary hammer, and then you can take it apart and then store it for next year. Or you can use it in the winter time and throw snowballs with it. Or you can use it in the summertime and use it for water balloons. You can use it again for candy at Halloween. But you don't need anything special. This is just ordinary duct tape. And then of course that will come off, and then you can put the spoon back after you wash it. Okay, I'm gonna try with this little piece of butterscotch. There's a roll of duct tape at 10 feet over there. And so we're gonna try this and see how it goes. And you pull back on this lever. There we go. So that's about 10 feet. So if I pull back on this lever a little bit further, it should go further. And it goes almost twice as far. So what's happening here is that when I pull back on this, there's potential energy being stored in this bungee cord. And when I let go, that potential energy gets converted into kinetic energy, and it makes the candy fly further. So the more potential in here, the more kinetic energy in there, and it makes it fly further away. And if I don't pull back that far, then it doesn't go that far. The other concept at play here is inertia. So you'll notice that when I do this, the lever stops because of this bar here, and the spoon stays in place because it's taped in. But the candy is just sitting here loose, and so when it stops here, the candy goes flying. And that's inertia, because an object at rest tends to stay at rest, and an object in motion tends to stay at motion. So this right here stops the bar, but since the candy is going, it stays going. That's inertia. That's why when you're in your car, you want to stay belted in, because if you don't, when the car stops, you would go flying. And that's inertia.